The topic we're going to be discussing for the next few videos is logic. Logic is all about statements. So we first have to talk about what a statement is. So a statement is a sentence or mathematical expression that is either true or false. So that means that we know it is definitely either true or false. We might not know which one of the two it is, but we know for sure that it is either true or false. That's what a statement is. So some examples. Here first are some examples of true statements. So this is one true statement. If a circle has radius r, then its area is pi r squared. That is a statement. It is making a claim that is true or false. In this case, it happens to be true, and that's a statement. So notice this is a sentence, and this is a special type of sentence known as a statement. Okay. This is a mathematical expression, and this happens to be a statement, and it happens to be a true statement. -2 is an element of z. -2 is an integer. So again, this is a mathematical expression, and since it is either true or false, it is a statement, and this happens to be a true statement. Here are some false statements. 2 + 2 = 5. So it's a statement. It is something that is definitely either true or false, but it is a false statement. -2 is an element of the natural numbers. That's again, it's something that's definitely either true or false. So therefore it's a statement, and it happens to be false, so it's a false statement. Now here are some statements whose truth value is unknown. Well, just one example of this. We'll see some more examples later. Statements whose truth value is unknown. So here's one. It will rain in Brooklyn in exactly 1 year from today. So the truth value of this is unknown. In a year from now, we might know the answer to this. But right now, the truth value is unknown. But it's definitely either true or false. That's the point, right? It's definitely either true or false. It's in a year from today, it is definitely either going to rain or not rain in Brooklyn. So it is something that is definitely either true or false. So therefore, it is a statement. But we don't know its truth value. Its truth value is unknown. Okay, we'll see some more examples of that soon. And then here are some things that are not statements. Okay, because these are going to be things that aren't either true or false. There's some other kind of sentences. Hello, all right, that's not true or false. It's just it's just a sentence. What time is it? It's a question, it's a type of sentence, but it's not making a claim. So it's not either true or false. Add 5 to both sides. That's a command, it's a type of sentence, but it's not a statement. Now, some notation, we often use letters like P, Q, R, or S to stand for sentences. For example, we can write this. So we can say, this is a way of saying that P stands for the sentence, the set n is infinite. Okay, the set n is infinite is a sentence. It also happens to be a statement because it is definitely either true or false, and it happens to be a true statement, right? It is the true statement. The set n is infinite. But the point is, more generally, it's a sentence, and we can use a letter like P or any letter. Usually, we use capital letters to stand for a sentence. So we can write like this, or we can write like this: P equals this sentence, right? Either way, what we're saying is that P stands for the sentence. And as we said, P is a true statement. More notation. When a sentence P contains a variable X, we often denote the sentence as P of X, like this. If P contains 2 variables, say X and Y, we can write it as P of X, Y, and so on. Right, so if you have 3 variables, you'd have P of X, Y, Z, and so on. So for example, here's an example of a sentence. P of X stands for the following sentence. If an integer X is a multiple of 6, then X is even. Again, if you have an integer X, that is a multiple of 6. So what's a multiple of 6? So those are things like one, those are things, not one. Those are things like 6, 12, 18, 24, and so on, right? Things that are multiples of 6. So if an integer x is a multiple of 6, then x is even. Okay, so now P of x is a true statement, since it is true no matter what value x has, right? It is true, in other words, no matter what x is. If you have an integer x that is a multiple of 6, no matter what x is, it's going to be true that x is even. So therefore, P of x is a true statement. But now consider this sentence. Q of x, which says the following, that here's the sentence, x is even. That's the sentence. So question, is Q of x, well, is it a statement? So first we'll note Q of 4 is a true statement, right? Because what does that mean? That means, what does Q of 4 mean? Well, if we plug 4 in for x, what it's saying is that 4 is even, and that's true, 4 is even. So that's a true statement. How about Q of 7? Well, Q of 7 is saying that 7 is even, but that's not true. That's a false statement. But again, it's something that is definitely either true or false, right? When I say 7 is even, that is a sentence that is definitely either true or false, and it happens to be false. Okay, so it's a false statement. But what about Q of x itself? Right, not Q of 4, not Q of 7. What about Q of x? The Q of x is not a statement, since its truth value depends on the value of x. Okay, so this is an important point. It's not a statement at all. It's not like it's different from something where we just don't know whether it's true or not, right? It's not an issue of us knowing. The issue is it depends on the value of x, and it's not so we don't consider this a statement. Okay, we don't consider this a statement. Okay, so this is what do we call such a thing? In other words, what do we call something like Q of x, whose truth value depends on the value of x? So we call this an open sentence. A sentence whose truth value depends on the value of one or more variables is called an open sentence. So here's an interesting example involving a statement. So there's something called the Goldbach Conjecture. Okay, there's some mathematician named Goldbach, and he had the following conjecture. Every even integer greater than 2 is the sum of 2 prime numbers. Okay, so you can take any even integer greater than 2, it's going to automatically be the sum of 2 prime numbers. That's what the claim is. That's what the claim is. Okay, it's not stated as a fact, it's stated as a claim. So here are some examples. Let's see if it sounds reasonable. So let's say we take the number 4. It's an even integer that is greater than 2. Is it the sum of 2 prime numbers? Answer, yes. So it is equal to 2 plus 2, and 2 is a prime number. So you have 2 prime number, it's a sum of 2 prime numbers. It doesn't have to be 2 different prime numbers, right? It's just 2 prime numbers. So you have 1 prime number and a second prime number. They could be the same prime number. That's fine. 6, how about 6? So is it the sum of 2 prime numbers? Yes, because it is equal to 3 plus 3. How about 8? Is it the sum of 2 prime numbers? Yes, because it is equal to 3 plus 5. How about 10? Is it the sum of 2 prime numbers? Yes. How about 12? Is it the sum of 2 prime numbers? Yes. Okay, so let's ask, is the Goldbach conjecture a statement? Before we ask whether it's true or not, is it a statement? Is it making a claim that is either true or false? So the answer is yes. It's making a claim. It's saying that for every even integer greater than 2, you can write that integer as the sum of 2 prime numbers. That is either true or false. So it is a statement. Question, is the Goldbach conjecture true? Answer is nobody knows. Right, and this is a very important point. Even though we had a bunch of examples that seem to line up with the Goldbach conjecture, and they do line up with the Goldbach conjecture, but we don't know that it's true for all cases, right? It's true for these examples. In fact, it's been checked for many, 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 many examples, but we haven't come up yet with a proof that it is true in all cases. In other words, we haven't shown that it is true for every even integer greater than 2. So no one knows if the Goldbach conjecture is true. You can write a program, for example, to test the Goldbach conjecture for really large, for starting from 2 and going up to starting from 4 and going up to really large numbers. But that wouldn't prove it. Even if that wouldn't prove it, because you wouldn't cover all possibilities in your program, right? Because there's always a bigger number. So okay, so we don't know if it's true. All right, another similar type of example. So consider the following function. F of n is defined as follows. So if n is even, then f of n is equal to n divided by 2. Okay, so let's say f of 6 is even, so that would be 3. Otherwise, if n is odd, then f of n is equal to 3 times n plus 1. Okay, so that's the function. Now here's something called the Collapse Conjecture. It says the following: if we start with any positive integer, so take any positive integer and apply f to it, and then apply f to the result, and then apply f to that result, and so on, the conjecture says that we will eventually arrive at the number 1. Okay, so this is interesting. So let's try some examples. So let's say we start with the number 5, the positive integer. Let's apply the function. So 5 is odd, so we're going to do 3 times 5 plus 1, which will be 16. Then we have to apply f to 16. So 16 is even, so we'll do 16 divided by 2, which is 8. Then we'll apply f again to this, and we'll get 4. We'll apply f again, and we'll get 2. We'll apply f again, and we'll get 1. So we ended up at 1. Let's try another example. Let's say we start with 6. Okay, so we have 6. 6 is even, so we apply f, we get 3, then 10, then 5, then 16, then 8, then 4, then 2, and finally 1. So we reached 1. We got to 1. We arrived at 1. Try one more example. We start at 11. So we start at 11. That leads to 34, 17, 52, 26, 30, 13, 40, 20, 10, 5, 16, 8, 4, 2, and finally 1. Okay, so these examples, it works for these examples, but we don't, these are just some examples. The conjecture claims that this is true for every positive integer, right? It says you can take any positive integer you want. So, we've shown that it works for 3 particular positive integers, but the claim is that it works for anyone that you might want to pick. So first let's ask, is the Collapse conjecture a statement? Okay, is it a statement? Is it making a claim that is either true or false? And the answer is yes, it's claiming something, and that claim is either true or false. We haven't shown that it's true, we haven't shown that it's false, but it is either true or false. So it is a statement. Is the Collapse conjecture true, though? Nobody knows. And in fact, if we ever know, we probably won't know for a very long time. Okay, you can read about it. You can read about this, but many mathematicians believe that current mathematics doesn't have a way to prove or disprove the Collapse conjecture. Well, to disprove it would be, easy. You just have to find an example. Well, not easy. It would be simpler to disprove, but let's assume, even if we think it's true, but to prove that it's true seems to be out of the reach of current mathematics. Anyways, you can read about this online and stuff. So that's a little interesting example of 2 interesting examples of statements, things that are statements whose truth values are unknown.